This is a video about implicit differentiation. So first, why would we need implicit differentiation? So this problem is going to motivate us to find implicit differentiation. So first, let's say we want to find the slope of the tangent line to the circle x squared plus y squared equals 32 at the point 4, 4. So first, if I want to find the slope to the tangent line, I would need to have an equation that says y equals, because everything that we've done so far has an equation where it's y equals. So I would have to find y. I'm going to solve for y. First, by solving for y squared, it would be 32 minus x squared. And then y would be equal to plus or minus the square root of 32 minus x squared. So let's say we just need to look at the top half of the circle, since the point 4, 4 is on the top half of the circle. So we're going to say y equals the square root of 32 minus x squared for the top semicircle. Or in other words, we're doing just this circle right here. So now we have a function of y. If we have a function of y, we know how to go about finding the slope for the tangent line. We need to find the derivative of y. So we could say dy dx is equal to, let's see, to find this, it would probably be easier if I rewrite y as 32 minus x squared raised to the power of 1/2. So to find this derivative, I'm going to use the chain rule. I like to draw in my little box. So I'd have a box around 32 minus x squared. That would be my inside function. So I need to take the derivative of the outside. So it's going to be 1/2 times whatever is inside my box. Keep that the same. And drop your power by 1. So from 1/2 minus 1 gives me negative 1/2. Times, now I need the derivative of the inside. The derivative of 32 minus x squared would be negative 2x. Let's simplify a little bit. My 2's cancel, so I'm going to get negative x. Let's bring our square root down to the bottom since that's the negative exponent. So negative x over 32 minus x squared. So that's my nice derivative, dy dx. And we could say my slope at x equals 4, since I wanted at the point 4, 4, is going to be negative 4 over the square root of 32 minus 4 squared, which is negative 4 over the square root of 16, or negative 1. So that's my final slope of the circle at the point 4, 4. This wasn't actually that bad to do, but it does involve a bunch of algebra, and for a more complicated problem it would be very difficult. So this is what we call explicit differentiation. I found y. I took the derivative like normal. This was explicit differentiation. So now for part 2, we're going to do the same problem using implicit differentiation. This allows us to do it quite a bit more simply with less steps. So in this problem, we start with our implicit equation. That's a function of x and y. And we say, okay, we're just going to go through it and we're going to take the derivative like normal, with one exception. What do we do when we get to the y? So let's take the derivative of x squared. That would just be 2x. And then I take the derivative of y squared, and that would normally be 2y. But there's a problem here. The problem is, even though we don't see it, y is truly a function of x. Look up above. Y is actually a function of x. Here is what y is. Y is, again, a function of x. And we're saying we don't actually know what the derivative of y is. We know it's not just going to be 2y here. We need to do the chain rule. Okay? So the chain rule says that y itself is kind of the inside of the box. We don't actually know what y is, but we know that it does have some function. So what we're going to do is we did the derivative of the outside. That gives us the 2y. Now I have to times it by the derivative of the inside. So this was derivative of the outside for the chain rule. Now I need times it by the derivative of the inside. And we're saying we know it's some function of x, but we don't actually know what. So what we're going to do is we're just going to say it's dy over dx. So we just do 2y times dy over dx equal to, now take the derivative of 32. The derivative of 32 is just 0. So at this point, we have 2x plus 2y times dy dx equals 0. This is called our implicit differentiation. At this point, because our final goal was to find dy dx, we're now going to solve for dy dx. To do this, we usually move all the terms that have dy dx in them to the left side of the equation, move all the terms that don't to the right side of the equation. So we'll have 2y times dy dx equals negative 2x, and then we'll divide both sides by 2y. Or negative x over y. And so my final answer here is that dx dy equals negative x over y. Now, this is not required, but if you are curious, you can go back up to what we did in part 1, where we actually solved for y. Y is the square root of 32 minus x squared. And I could plug that in here. So again, not necessary, but I could say, okay, oh, I'm sorry, I wrote this wrong here. Dy dx. So I could say dy dx is equal to negative x over, now if I take y from up above, y was the square root of 32 minus x squared. Look up above. That's the same thing we got for dy dx up above. Okay. Notice it gives us the same answer. But we don't usually actually have to do that. That's unnecessary to do that actual step. Instead, we'll just stick with dy dx equals negative x over y. And now if we're trying to find the slope, so the slope at the point 4, 4 is going to be negative 4 over 4, since x is 4 and y is 4, or negative 1. So my slope to the circle at the point 4, 4 is negative 1. So part 2 will be, or doing it like we did in part 2 with implicit differentiation, will be much nicer, simpler, with less arithmetic and less algebra that we have to do. Now in our next example, let's find dy dx, or find the derivative of y with respect to x. If we have this equation, notice this equation, it would be very difficult to get y by itself because we have a y cubed and a y squared. Explicit differentiation would be very, very difficult. So let's go ahead and use implicit differentiation, where again we take the derivative of each term like we normally would, but whenever we see y, we have to tack on the expression dy dx. So I'm going to take the derivative just like I normally would. So 4y cubed, this would be 4 times 3 y squared. But y is really a function of x. We have no idea what it is, but it is some function. It's kind of like there's a box around our y. So whenever we take the derivative of y, we just tack on dy dx. If you want, you get to the point where you say, okay, without any thinking about it, as soon as I take the derivative of y, I tack on dy dx. Okay, minus, now take the derivative of x squared, so just negative 2x, plus the derivative of 2x is 2, equals 9y squared, so that would be 9 times 2y, but we took the derivative of y, so we have to tack on dy dx. The reason we know that we need to do this is we're looking for the derivative of y with respect to x. We know that because of what they asked us to find, dy dx. So that says whenever you take a y, you have to tack on the derivative of dy dx. Now we can go through and simplify. What we're going to want to do is move all the terms that have a dy dx to the left side of the equation. So we're going to have 12y squared times dy dx minus 18y times dy dx equals 2x minus 2. At this point, it's usually simpler if we factor out dy dx. So it's going to be dy dx times 12y squared minus 18y equals 2x minus 2. And then we're going to divide both sides by 12y squared minus 18y. And at this point, I would probably go through and just divide everything by 2 since it looks like I can. So 2x divided by 2 is x minus 1 over 6y squared minus 9y. And that's okay because I divided everything by 2. And this is my final answer.